All right. Hello, grade 12s. Today's lesson is actually kind of an interesting one. Um, we're just going to do this one example. We're just going to do this one extra electric field example today. So if you are still working on those practice problems from the last couple lessons, that's totally fine. Just follow along with this one extra example. It'll give you an idea of how to do another type that we can run into. This one's kind of tricky. I know I keep saying that, but the fact is that there are tricky types of questions in this unit. So we'll just do this one. It shouldn't take me much longer than maybe 10 or so minutes, hopefully. I always say that, and then my videos end up being 20 minutes. So I'll try to keep it somewhat brief for today. Now, let's take a look. Let's just jump right into it. So we have got a positive 5 microcoulomb charge, we'll call it charge A, is 40 centimeters to the left of a positive 4 microcoulomb charge, we'll call it charge B. There's a location between these two, and this makes sense. Like theoretically, this should always happen. There should always be a place between these two where the net electric field is going to be equal to 0. So what that means is that there's a point where the electric field from A is equal and opposite to the electric field from B. And now that's not going to fall right in between the two of them, right? Because their charges are different sizes. So if I draw this out, let's use our charges in green here. You've got one charge there, we'll call it A, positive. And then you've got another charge over here, positive as well, we'll call it B. Now you've got a total distance between these two, right? You've got a total distance between these two. Let's do this in a different color. Let's say we'll go from middle or the closest side. So you've got a distance here that is 40 centimeters. So that'll be like our total distance. We'll convert that. I'm not going to call it R. I'll show you why I'm not going to call it R. But that total distance, maybe we'll call it D, is going to be equal to 0.4 meters, right? We'll convert it just right now. We'll convert it to meters. And we'll just write all this stuff down that we know. QA is 5 times 10 to the negative 6 coulombs. So you get really used to that conversion, the micro. And QB is 4 times 10 to the negative 6 coulombs. So this distance right here is 0.4. But because there are two different sizes of charges, this point in between the two of them is not going to be right in the center. It's not going to be at 0.2. It's going to be somewhere a little bit closer to B, right? Because B has a smaller charge. So B is going to be giving off a smaller electric field. So the point is going to be somewhere a little bit closer to B. So what that ends up giving us is two extra distances here that we don't know. We've got a distance between B and the spot where we'll call this spot right here. This spot we'll call E equals 0, right? Because the total net electric field there is going to be equal to 0. That's what we said. So we've got a spot there. Now, let's just label these. I'm going to call this one R, and I'm going to call this one the distance between A and the spot where E equals 0. I'm going to call it big R. Okay, so we've got an uppercase R and a lowercase r. That's really all the information that we've been given, and that's enough. We're going to use the formula that electric field at point A, or due to point charge A, at this point right here is going to be equal to the electric field due to point charge B. So let's write down what that looks like if we actually start to replace these with our formulas. So K QA over capital or uppercase R is equal to K QB over lowercase r. So that's the charge from A, right? That's creating that field because of A, and the distance, uppercase R, which is the distance to the E equals 0 point. Now we've got an immediate cancellation here. We've got a K value, right? We got Coulomb's constant that we can just cancel out right away because it's in both terms. But now we've got a problem, right? Because now we know QA and we know QB, but we don't know R or R. So we have two knowns and two unknowns. So here's where a little tricky kind of sidestep occurs. And this is going to help us to solve the problem. We know that the total distance, it's a really simple formula. We know that the total distance between them is 0.4. And 0.4 is made up of uppercase R combined with lowercase r, right? R plus R. So what we're going to do is we're going to do like a substitution type of idea that we would have done back when we were doing momentum and dynamics, I think is when we did the substitution. R, let's solve for R. Let's solve for uppercase R. Uppercase R is 0.4 minus lowercase r. So what you do then is you take this 0.4 minus, and you plug it in right there, right? You can replace that R with 0.4 minus R. What you get if you do that is QA, remember we canceled out our Coulomb constants, 0.4 minus R squared equals QB over R squared. So now we only have one unknown. We know QA and we know QB, but we don't know R. It might seem like we're in the clear, but there's one other tricky part to this question. So what I'm going to do is I'm going to move my 0.4 minus r squared up to this side, and I'm going to move my r squared up to this side. This is just trying to get rid of having denominators, right? So we'll end up with QA r squared equals QB 0.4 minus r squared. And now what we realize is, you know what? Let's not jump ahead of ourselves here. Let's plug in what QA is. So QA is 5 times 10 to the negative 6 r squared equals 4 times 10 to the negative 6. That's QB times. Let's actually write out here. Let's do another little side thing here. What is 0.4 r squared? Let's do that right now. 0.4 r squared is technically 0.4 minus r. 0.4 minus r times 0.4 minus r. So 0.4 is multiplied by each other to give us 0.16 minus 0.4r minus 0.4r, right? So we get minus 0.8r, and then minus r times minus r is positive r squared. So what we're going to notice here now is that it's not as easy as we thought it would be, and then we plug it right down. We're going to end up with a situation in which, unfortunately, we have to use the quadratic formula. Because I'm gonna multiply this by this. I'm gonna multiply this through all of these terms. I'm gonna do it. I have it written right here because I've already done it before. So 5 times 10 to the negative 6 r squared, and then 4 times 10 to the negative 6 times 0.16 gives us 6.4 times 10 to the negative 7 minus 4 times 10 to the negative 6 multiplied by 0.8r is 3.2 times 10 to the negative 6r. And then plus r squared. So 4 times 10 to the negative 6 r squared. Now, throw back to basically, I don't know, any math course that you've done, maybe I think grade 9 math, we do this when we combine our like terms. You've got a couple r squareds and then an r and just a value. So 5 times 10 to the negative 6 minus 4 times 10 to the negative 6, because I'm going to move it to this side, give me 1 times 10 to the negative 6 r squared. So that was 5 minus the 4 there, right? Moving it to this side. I want to move everything to one side because I'm setting up here for, unfortunately, the quadratic formula. Quadratic formula is needed, right? We look at this, we can't solve that. Can't solve that, the quadratic formula. So we'll move this to the other side. So positive plus 3.2 times 10 to the negative 6r, and then move this to the other side, and we get negative 6.4 or minus 6.4 times 10 to the negative 7 equals 0. So we've tried to avoid it as much as we can using the quadratic formula. I myself also try to avoid it as much as I can. I think that there's other ways to do it, but in this case, it's pretty unavoidable. So we'll just do it. We know how to do it. We've got this part right here. This is A, right? This is B. I got a little bit. It doesn't include, right? It's ax squared plus bx plus c equals 0, right? That's the quadratic formula. That's how we set it up. And then remember, I don't know, maybe you can, maybe you can't remember it off the top of your head what the quadratic formula actually is. We're trying to find r, so that's what it's going to be equal to. So r equals negative b plus or minus the square root of b squared minus 4ac. I'm using lowercase letters now. I don't know why I used uppercase here. Should be a, should be b, should be c. And again, my video is probably going to end up being way longer than I wanted it to be. Divided by 2a. That is the quadratic formula. So we can remember it, okay? So now all that's left to do is just plug in our B where we need to, our A where we need to, and our C where we need to, and we should get the right answer. So R equals negative B, so 3.2 times 10 to the negative 6. Oh my goodness, they're probably from here. Plus or minus, I'm going to have to start writing a little bit smaller. Plus or minus B squared, so 3.2 times 10 to the negative 6 squared minus 4 times a, 1 times 10 to the negative 6 c, which is negative 6.4. I should have my underline under here. Negative 6.4 times 10 to the negative 7. My mouse is in the way. Negative 6.4 times 10 to the negative 7. All of that under the square root. And then divide all of that by 2 times 1 times 10 to the negative 6, which is a. I almost ran out of room there, but we got it done. So let's just find r. I mean, now is time to do that. So what I would do is I would do all of the stuff under here first, then take the square root, and then do this plus or minus that divided by that. Now, you're either going to get, this is the thing with the plus or minus, you're going to get two different answers. You're either going to get 0.189 meters, or you're going to get negative 3.39 meters. Now, this one, obviously, in our scenario, having a negative distance there does not make sense. So that's good. There's your answer. Your answer is that the distance from B to that location is 0.189 meters. Now, if you wanted to find what the other one was, you'd say, right, remember R is equal to 0.4 minus 0.189, right? That was the relationship that we had up here, because the total distance between them was 0.4. So we take 0.4, and we subtract 0.189, and we get 0.211. So there's your two answers that you could have got. If you solved for uppercase R, you could have got that as well. Either of those are fine, but that's it. So that is a pretty tricky one. There's lots of steps involved there. You got the quadratic formula that you need to use, and you've got some substitution to use as well. So you've got a couple different things that are going to maybe trip you up when you're trying to do that. So make sure you're taking questions like that slowly, and you're doing them one step at a time, not trying to get ahead of yourself. Okay. So good luck with the rest of the questions. Have a great rest of your day, and I'll talk to you tomorrow.